All right, here we go. Um, we're going to finish the notes today. We're going to finish the notes today. Yep. We're on example 8. All right. So remember, the first part of your test, which is on Tuesday, is proving like 4 out of 5 identities using just the fundamental identities. That's just the identities from 6.1. Then you have a middle section where you're solving equations, and I think you're doing all 3 of them. There's no like escape valve. You're doing 3 of them, and it includes all the identities. So that would be what we're doing right here. And then the last part, I think you're doing 3 out of 4 identities using all the identities that we've learned, including all the half angles and double angles and stuff like that, power reducing. So this right here, starting in example 8, is like middle section stuff, okay? Remember, on Monday, you're going to be in here taking a practice exam with some warm body. Mr. Peck couldn't free up his schedule, so it'll be somebody. And if you have any questions while you're working, you can run next door and ask Mrs. Lincoln or Mrs. Skurhawk, either one of them. I'm sorry, I tried. He tried, but it didn't work. And then on Tuesday, you'll just have a warm body handing you a piece of paper. And be ready to go as soon as you come in on Tuesday because we want to let you have as much time as possible. So no cramming with your identities before. Maybe we'll tell the sub just to hand you the test as you walk in. That sounds good. Okay, now we can start. If you have a little bit if you get here quickly with passing periods, you can have a little bonus time. Okay. All right, example 8, solve algebraically in the interval from 0 to 2 pi. So remember, solving means it's a conditional equation, and we're trying to find the values of x, and when we plug into both sides, make it work. We are limiting ourselves to 1 rotation around the unit circle, which is, again, what I call our comfort zone, our wheelhouse. That's where we've quizzed over the angles. So sine of 2x equals cosine x. All right, so we've already been solving some of these equations using the fundamental identities. I think I'm coughing up all the dust from that projector now. New pneumonia, right? You almost like you're stuttering. New pneumonia. Remember the Zach's back. Remember that the strategy for solving is the following. If you have more than one term with a variable in it, your goal is to get everything on one side and set it equal to 0. If you have just a single term with a variable in it, you want to isolate it. So how many terms do we have with variables in this equation? 2. One on the left, if we're counting individual sides, one on the left and one on the right. So in this case, your first step could be, and there's several first steps, but your first step could be to bring the cosine across and set it equal to 0. You don't want to divide both sides by cosine because then it'll be 1 on the right-hand side. All right, you just subtract it from both sides. And we typically do that on the left, but you could have done cosine minus 2x as well. Now that it's equal to 0, we look for a common factor. Is x a common factor? No, sillies. That's an angle, okay? Angles are essentially off limits unless you use identity. So, much like a proof, your primary goal before after you get everything on one side, and it could have been your first step, is to get the angles the same. You have to get the angles the same. So we can either build up a single x to try to make it a 2x, no thank you, or tear down a 2x and put it in terms of 1x. Tear it down. So do we have a double angle identity for sine? Indeed we do. Yes, and very good. Now it's like spewing out before you even ask for it, like, right? Because now you want to share your knowledge of these identities because you've memorized them. 2 sine x cosine of x. Perfect. And you see how if you didn't know that identity, you'd just be staring at that line saying, man, I guess I'm going to fail. Right? Yeah, you don't want to do that. Sine of 2x is 2 sine x cosine x. Now do we have a common factor? Indeed. Now we have a cosine of x that is common in both. So we shall now factor out that cosine of x. And remember, if you start with 2 terms and you factor something out, how many terms are you going to be left with? Still 2. Good. So we're left with 2 sine of x. And for some reason, a lot of people stop there. Like, oh, the cosine's gone. No, it's minus 1. And if, again, you mentally redistribute, you could catch that careless mistake. Now that I have 2 factors, I'll set them both equal to 0. So cosine of x equals 0, or 2 sine of x minus 1 equals 0. All right, so now cosine of x is equal to 0. That one's ready to go. In the second equation, now we have just a single variable term, so our goal is to isolate it. And if you bring the 1 across and divide by 3, you get sine of x is a half. And now it's everybody's favorite time. It's unit circle time, or time circle unit if you want, right? Time circle unit, because we're using the unit circle backwards, right? Yeah. Bless you. So now where within one rotation is cosine equal to 0? Cosine of 0 is 1. Pi halves and 3 pi halves. Good. So you got another unit circle because cosine of both of those is 0. Sweet. And then over here, where is sine equal to 1 half? Sine y, right? So that's going to be quadrants 1 and 2. And that's your pi 6 or pi thirds reference angle? Pi 6. So one of them's got to be pi 6 and the other one is 5 pi 6. Muy bien, bien. All right. So how many solutions does this dude have? Quattro for fear. Fear? No, we don't fear anything anymore. We got our unit circle memorized and we have our identities memorized. So fear in English? No. Fear in German? Yeah, 4 solutions. Okay. All right. See, that's not bad, right? If that were one question on the test, you'd be like, I got this, man. I'm not failing. I'm succeeding. I care, right? I-C-A-R-E. Okay. Any comments on that one? Like remarks? Like, I kind of like that one, right? That one made me feel good about myself. I discovered something about myself on that one. I think I'm going to go home and write about this one in my diary. Journal. We call it a journal now, right? Blog? I'm going to blog about that one. Okay. All right. Good. So nothing to it, right? How many more? Oh, we got some more. Okay, let's go. Number 9. Example 9. Solve, not prove. All right. So if the instructions say solve and you're drawing a line down the middle, oh my gosh, I think you can all agree that that is comical, right? Humorous? Yeah. If at this point it says solve and you're drawing a line down the middle, you have been tuning out, right? Because we only do that when the instructions say what? Prove, right? When it's solve, we need to find the values that make it true. So notice we have a sine squared of x and a 2 sine squared of a half angle x. So you have 2 options for your first step. You can either A, try to get the angles the same, or B, because we have 2 variable terms, we can get everything on one side and set it equal to 0. The sequence doesn't matter. You're going to have to do both. What do y'all want to do first? Set it equal to 0. That's probably a very good first thing to just establish as a routine. If you have more than one variable term, get everything on one side, set it equal to 0. Because now you're looking to factor. And notice they're both sine squared, but there's nothing common because the angles are not the same. So just like in a proof, our goal is to get the angles the same. Do you want to try to build up an x to make it an x halves? Or quote unquote tear down an x halves to make it an x? Tear it down, right. Really, but when we tear down an x halves, we're really building it up to an x, right? But I say tear down, quote unquote, because we have an identity for that. Now, this one is interesting because notice you can either use the half angle identity, which would be plus or minus the radical, and then notice it's squared, right? So when you square the radical, it would go away. Or you can use the power reducing identity. It doesn't really matter. What would you probably be inclined to do? They both work. Power reducing? Yeah. Let's look at it from the power reducing perspective, okay? When you reduce the power by a factor of 2, you do what to the angle? Double it, right? It's the same scale factor. You half the power, you double the angle. You half the power, you double the angle. So using the power reducing identity, it's going to be 1/2 times 1 sine is minus, right? Cosine of twice the angle. What's twice x halves? X, right? So that's what it would look like from the power reducing identity, the PRI, which we don't really call that. Or, I'll just write it underneath here, if you envision that like this, If you see that as sine squared and you see that as sine as x halves, because really that's another way to write sine squared, correct? If you don't use the power reducing identity, you can use the half angle identity. Let's see what that would look like. That would be sine squared minus 2. And now in the brackets, you're going to have plus or minus the square root of 1/2 times 1 minus cosine of x. And then, of course, on the line after that, what happens when you square a radical? It goes away, right? So you're left with just sine squared of x minus 2 times the radicand, 1/2 times 1 minus cosine x. And notice you get to the same thing. It's just a little bit more scenic and a lot more radical, right? Am I right? Okay. There's more than one way to eat a Reese's peanut butter cup, and there's more than one way to do these equations, proofs, solving, okay? So at any rate, we're down here. Now, what I did lose when I did it my other way is equaling to 0. So once you set it equal to 0, you need to keep it equal to 0. It's got to be an equation, otherwise you lose perspective, okay? All right, now let's go ahead and see what we got here. We got the angles the same, so now it's like, yes. But if we can find the like terms, we got 2 times 1/2, that's just 1. Now here's where you got to be careful. We get a -1 out front, but it's still times the quantity 1 minus cosine. So guess what we need to do with that negative? Distribute it. Sine squared of x minus 1 plus cosine of x equals 0. And now you look for a common factor. Now we're kind of back in 6.1, fundamental identities. The angles are the same. I got a squared term, I got a non-squared term, and I have a constant. Can I factor that as a trinomial? And this is going to show up a lot in your equation. You're going to have one like this, I promise. We need to make them, now that the angles are the same, since there's a trinomial, we need to make them in terms of either sine or cosine. How do we do that? Papa Kid. It's real easy to change a sine squared into a cosine squared. So let's put parentheses around sine squared and call it 1 minus cosine squared. Now in this case, you don't really need parentheses because there's nothing to distribute other than a 1. But if there had been a negative in front of it, you would need to distribute it. Okay? So now let's combine like terms, and we'll write it in descending order. We get a negative cosine squared, and then, what happens with the 1s? They actually cancel. Holy moly smokers. And so it turns out that we don't have to factor a trinomial. Oh, instead, because the constant's gone, now we can just pull out a what? A cosine, a common factor. Okay, had the 1 remained, we would have factored it, okay? We would have factored it like this, but we don't have to do that. So now we can just pull out a cosine of x, and we're left with negative cosine of x plus 1. Negative cosine x plus 1. If you don't like leading with the negative, I understand. I'm a product of Rachel's challenge myself. So you can insulate the negative and bury it in the middle, right? So you can flip those terms around. Same thing, yes? Negative cosine, yeah. It just looks better. It looks more proper. Now we can set each equal to 0. Cosine of x equals 0, or 1 minus cosine of x equals 0. And if I solve the other one, that means cosine of x equals 1. If I bring that across, I get 1 equals cosine of x, which is the same as cosine x equals 1. And now it's everybody's favorite time. Time, circle, unit, time. Yeah, unit, circle, time. Very good. So where is cosine equal to 0? Pi halves and 3 pi halves. We just said that. And now where is cosine equal to 1? Pi is -1. 2 pi? Right, 2 pi is outside of our interval. We want to keep it between 0 and 2 pi, so we'll just say 0, right. 2 pi is correct, but that starts the next rotation. It was this, remember. We're looking between 0 and 2 pi, and then not including 2 pi. Had that been a bracket around 2 pi, then we would have included 2 pi, okay? So it's important to look for that when we start. Where do we want our solutions? So this guy had 3. All right. Was that difficult? Challenging? No. Was it fun? Heck yeah. All right. Inch by inch, it's a cinch, right? And that's all we have to do. One line at a time. One step at a time. Okay. Comments or questions on that one? Is that blog worthy? Blog worthy? Like to write about in your blog? Like, yeah, put that in the blogosphere. The other day I was solving this trigonometric equation, and much to my chagrin, right? That's the kind of words you read in a blog. Oh, it says find all solutions in radians. Holy moly. When in doubt, read the instructions. Oh my gosh. Okay, we got this. We got this. On the test, I'm going to have you solve it between 0 and 2 pi. Okay, so these would be the answers. But when it says to find all of them, remember, all we have to do is find all the ones between 0 and 2 pi and do what to the end of each of them? How do we get all the others that land at the same spot but are multiple rotations away? Add full rotation multiples, right? So 2 pi n plus 2 pi n plus 2 pi n. And I'll make one blanket statement here. Blankets are good for covering up with when you're cold. That's a blanket statement. Here's another blanket statement. N is in the integers, okay? Y'all have heard of the term blanket statement? It's not necessarily a statement about a blanket. It's a statement that covers a lot of things, right? So the N is for all three. Okay, cool. So that's not a big deal. You just find all of them between 0 and 2 pi, and then plus coterminal angles, right? 2 pi n, 2 pi n. All right. When in doubt, read the instructions, right? It's not the most macho thing to do, guys, right? To read the instructions first. Guy, we can figure this out by ourselves. And then you end up with like a lot of extra parts when you're done. You're like, phew, probably should have read the instructions. Okay. Like putting together something from IKEA, you know. That's how arguments start. Example 10. Example 10. Solve the following equations in the interval from 0 to 2 pi. Okay. This time we read the instructions first. So we're going to be in our wheelhouse, in our comfort zone. Okay. Y'all talk me through this one. Step 1 is what? Let's see. Read it, okay? 2, okay, all right. It's already equal to 0, right? If it's already equal to 0, do we have any common factors? No. There's how many terms have variables in it? Just the one, right? Just the one. So remember, the goal is to isolate it. We want to get the sine of 3x by itself. So if I add 1 and divide by 2, we get sine of 3x equals 1/2. Now, here is a very, 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 very important thing I'm going to tell you right now regarding these types of problems. You do not, I repeat, you do not have to get 3x down to single x in order to solve this. We've already isolated it. You can solve it as long as you can isolate the trig function. Now, if there were another term in there, like plus sine of 1x, now you're going to have to get the angles the same, and now you're going to have to tear down the 3x. But if he's the only dude in there, leave it as a 3x. Now, let me ask you this. What effect does the 3 have on the graph of sine of x? Sine of x looks like this, right, from 0 to 2 pi. Not vertical stretch, horizontal compression, right? You're going to have 3, that's your b value. You're going to have 3 cycles instead of just the 1, right? So if within 1 rotation, let's do this. If we were just looking at 1 rotation, pretend like that was just sine of 1x equals 1/2, okay? Pretend. What would x equal? Where does sine equal positive 1/2? It would be right here and right here. So we've already answered this today. What is it? Pi 6 and 5 pi 6, okay? If within 1 rotation we have 2 solutions, then if I compress it by a factor of 3, how many solutions am I going to have now on my graph from 0 to 2 pi? 6, right? Because each of those is going to have 3 solutions. So this number right here tells you how many solutions you have per root. Okay, so pi 6, which is the first one, is going to have 2 buddies, and 5 pi 6 is going to have 2 buddies. Now, how do we find those? It's this easy, okay? All you got to do is say, okay, it's going to be pi 6 and 5 pi 6. But instead of those equaling x, they're going to equal 3x. All right, 3x. Now, here's an option that you have. If you want to put plus 2 pi n, you can do that. That's an option you have. I would kind of recommend that. And now you have a system of equations. All you got to do is solve for x by multiplying everything through by 1/3. So what's 1/3 times pi 6? Pi 18ths, right? So that's essentially what happened to this first one. This one right here was at pi 6, and now we've compressed it by a factor of 3, so it's now at pi 18th. See what we're doing? Okay. And then we also can do this. What's 1/3 times 2 pi? 2 pi thirds. Guess what the new period is going to be of sine of 3x? Remember how we find the period? It's 2 pi over b. Guess what's 2 pi divided by 3? 2 pi thirds. So basically what that means then is if once you have pi 18ths, all you have to do to get the next one is add 2 pi thirds. See that? And then all you have to do to get the next one is add another 2 pi thirds. That make sense? Okay? And then we do the same thing for the other one. 5 pi 6, let me use green for this one. 5 pi 6, if you multiply by a third, is 5 pi 18ths. So this fella right here, he moved all the way over here. And now he's at 5 pi 18ths. Well, how am I going to get all of his buddies? Just add another 2 pi thirds, right? Okay, so once you have these are your generating equations. And we've done this before. So let's go ahead and generate them. Let's use the first one, okay? We know that each of these is going to have 3 solutions. So here we go. X equals, we know when n is 0, we get pi 18ths, all right? That's our first guy. Hey, pi 18ths, comma, what's a better version of 2 pi thirds if we're going to be adding it to 18ths? If we multiply by 6 over 6, we get 12 pi 18ths. That's another version of 2 pi thirds, right? So that's a good one to use. So now let's just add 12. What's 12 plus 1? 13 pi 18ths, okay? So that's going to give us this second guy right here, okay? That's this guy right here. And now to get that third guy, that is the root coming up, just add another 12. What's 13 plus 12? 25. And that's it. We know that we got 3, so we're done. That 3 was this 3 way up here. That tells you how many you're going to have per root, okay? So now we'll switch to the other fella. Let's come down here. Of course, when n is 0, we get 5 pi 18ths. Okay, so now that's hitting that root on the sine graph coming down. Okay, and now we just add 2 pi thirds to get the next one, which is 12 pi 18ths. So 5 plus 12 is 17 pi 18ths. So that's this guy here. And then we just do it one more time to get the third guy. 17 plus 12 is 29 pi 18ths. And again, we have the 3 of them. And so those are your 6 solutions. Pretty awesome, right? I think so. Pretty darn awesome. Okay, that's a very important type of problem. Let's do another one here. Oh gosh. Oh, notice there's only one variable term. So instead of setting it equal to 0, we'll isolate it. So I'm going to do this one in 2 steps. That's 2 cosine of x thirds equals negative square root of tree. And then I divide 2 by 2, and I get cosine of x thirds equals negative square root of tree over 2. What effect does replacing x with 1/3 x do to the graph of cosine? It's not a horizontal compression anymore, it's a horizontal stretch. Oh, so now between 0 and 2 pi, I may not see very many solutions, right? Because if cosine, if you want to imagine it, cosine originally looked like this. Here's 2 pi. And it was equal to negative square root of 3/2 twice. But if I'm going to take those and I'm going to put them 3 times further away, that graph now is getting stretched so far, man, maybe that first root happens outside of 2 pi? We'll see, right? We'll see. We'll let the math do the talking, okay? Because it's x thirds, and it's the only trig function we have, you do not have to get that to be an x. You just pretend that it's cosine of x. Where would cosine equal negative square root of 3 halves? That is, what are these two angles right there? Cosine's negative in quadrants 2 and 3, so that's going to be your pi 6 reference angle. 7 pi 6 is 1. I'm going to do them in order. Yeah, 5 pi 6 and 7 pi 6. Excellent. So that would be those first two guys. All right, and now we're just going to put plus 2 pi n, plus 2 pi n. And that's what you want to get in the habit of doing anytime you're solving with a multiple angle. Okay, if you're solving with a multiple angle, just put plus 2 pi n. And now instead of equaling x, you just set them equal to x thirds, or whatever it is inside there. Every solution is going to have a third of a solution, right, instead of 3. Now let's just solve. We'll just multiply through by 3. And so we get x equals, what's 3 times 5 pi 6? The 3 and the 6 divide out to give you 5 pi halves, right? Plus 3 times 2 is 6 pi. That's your new period. Wow. And then you do the next one. 7 pi 6 times 3. Again, 3, 6 divides out to give you 7 pi halves. Plus 3 times 2, that's 6 pi n. And now you have your generating equations. Your gen EQs. And again, we want our solutions between 0 and 2 pi. So let's go up to the first one and start generating. When n is 0, we get 5 pi halves. Is 5 pi halves between 0 and 2 pi? No, right? It's already bigger than 4 pi halves. So that's the smallest angle. That's where this first guy right here, this first guy, that's where he went. We can put him out here 3 times further away, and boom. That was now the first place where the graph hit going down, and it ends up being outside of 2 pi. So for sure, if I add 6 pi to that, it's going to be too big. And for sure, the next guy, if I look at 7 pi halves gets pushed way over here. So how many solutions do we have between 0 and 2 pi? No solutions. Okay? There are still infinitely many solutions, but none between 0 and 2 pi. So you can kind of see how compressing and stretching make a difference on a certain interval. Okay, how do y'all feel about that? Pretty good. Good, thank you. I'm going to save part C for tomorrow. That's a good Friday question. If you're on the diurnal, you might want to just watch the video over the weekend. Monday in class, you're going to be working a practice test. And again, Mrs. Lincoln and Ms. Skurhawk will be available to answer any questions you have. Tuesday's the test. So watch the video. That's great. Like, hey, friends, gather around. It's math time at the diurnal, right? When you're bored in the tent or something, right? Whatever.
I have an AP exam in the morning.
Okay. Okay. Good luck on it.
Thank you.
On a Friday. What is that one?
Microeconomics.
Micro. Oh, sweet. Is that like a small test? They give you like
I hope.
tiny sheets of paper?